You ever have a great idea for an app and wonder, how does that actually get made? Well, the biggest challenge really is taking that idea from our heads and turning it into a language a computer can actually understand. And in this explainer, we're going to break down exactly how that happens. I mean, think about it. How does an idea in your head become a real working app on your phone? This is the fundamental challenge for every developer. You're trying to bridge this huge gap between our creative, kind of messy human world and the super rigid, logical world of a computer's processor. It's the one problem that every single piece of software, from your calculator to the most complex game, has to solve. All right, so here's how we're going to build that bridge together. First, we'll tackle that human-computer language gap. Then, we'll meet the code translators that do all the heavy lifting. We'll get into a little showdown, compiler versus interpreter. After that, we'll take a peek at a programmer's digital toolbox. And finally, we'll talk about how you go about choosing the right language for the right job. Let's get into it. Okay, so at the very heart of all of this, you've got two completely different worlds. On one side, you have us, humans. We think in concepts and ideas, in language. But on the other side, you've got computers, and they only get one thing: electrical signals, ones and zeros. That's it. So yeah, you can see how there's a pretty massive communication gap we need to cross. And this is where programming languages come in. They are literally the bridge. So you have what are called high-level languages. Think Python, Java, C++. These use words and logic that feel, a lot more natural to us humans. Then, way down at the other end of the spectrum, you have the low-level languages. We're talking machine code, assembly. This stuff is the computer's native tongue. It's pure ones and zeros. It's super powerful, for sure, but trying to read it directly, it's almost impossible for us. So that's the big question, right? If we're writing in these nice high-level languages, but the computer only gets the low-level ones and zeros, how does that even work? Well, we need a translator. These are the special programs that do the real work, acting as that bridge and converting our instructions into something the machine can actually run with. Yeah, the definition is pretty straightforward, but it's dead on. A translator is a piece of software, and it has one single critical job: take the code that we write and turn it into the binary machine code that the computer's brain, the CPU, can actually execute. Without this crucial step, all our brilliant code is really just a useless text file. Now, there are basically three types of these translators. You've got compilers, interpreters, and assemblers. Assemblers are for those low-level assembly languages, but for the high-level stuff we're talking about, we're going to focus on the big two: compilers and interpreters. They both get the same job done, but, and this is key, they work in totally different ways. All right, let's dive into these two different styles of translation. So you've got compilers on one side and interpreters on the other. They both translate our code, sure, but their methods couldn't be more different. And it's really not a question of which one is better. It's all about which strategy is the right one for a specific situation, because each of them has its own pros and cons. Okay, so think of a compiler like this. It's a translator that decides to translate an entire book at once before anyone can read it. It takes your entire program, every single line, and chews on it, processing the whole thing in one big go. What it spits out is a brand new, totally separate file that's your executable program. And only when that whole translation is done can you actually run the thing. It's the all-at-once approach. Now, an interpreter? Totally different story. An interpreter is like having a live translator whispering in your ear at the UN. It doesn't translate the whole speech beforehand. Instead, it reads your code one line at a time, and as it reads each line, it translates and executes it right then and there. There's no separate executable file created. It's all happening live, on the fly. So this difference in how they work leads to a classic trade-off in software development. It's basically speed versus convenience. A compiled program, because all the translation work is done up front, runs way faster. That's a huge win for the end user. But an interpreted program, since it's translating as it goes, is naturally a bit slower. The flip side, for the developer writing the code, an interpreter is often a dream for debugging. Why? Because it tells you about an error the instant it hits that line. A compiler, on the other hand, makes you wait until it's tried to compile the whole thing before it just gives you a list of all your mistakes. Okay, so we've got the how covered. We know how code gets translated, but where does a programmer actually do all this work? I mean, they're not just typing in a simple notepad file. They use a really sophisticated digital workbench, and it's called an IDE. An IDE stands for Integrated Development Environment, and honestly, it's pretty much what it sounds like. It's this one central program that bundles together all the essential tools a developer needs. Think of it as their command center, their workbench. It's literally the program you use to write other programs. And a good IDE is just packed with stuff to make a programmer's life so much easier. You've got your code editor, but it's smart. It highlights your syntax with colors so you can actually read what you're doing. It has a built-in debugger to help you hunt down those annoying bugs. It usually integrates with version control, like Git, so you can track all your changes. And of course, it has buttons to build and run your code with just a single click. It's the whole package. And let me tell you, these tools are absolute game changers. Think that built-in debugger, for example. It allows a developer to literally pause their program in the middle of running, step through the code one line at a time, and inspect everything. What values are stored where. It gives you an X-ray view into your code. This just speeds up finding and fixing errors like you wouldn't believe.
All right, so we've built our bridge. We understand how an idea gets turned into an executable program. But that kind of brings up a new question, doesn't it? If we can just translate any of these languages, why are there so many of them? I mean, why not just pick one and stick with it?
Well, choosing a language is all about choosing the right tool from the toolbox for a specific job. For instance, are you building a high-performance, graphically intense video game? You're going to want speed, so you'll probably reach for a compiled language like C++. But what if you're analyzing massive data sets for scientific research? Then the flexibility of an interpreted language like Python, with all its amazing data libraries, is probably the smarter choice. And of course, there's the human factor. What languages does your team already know and love?
So here's the crucial point, the main takeaway. There is no single best programming language. That's like asking if a hammer is better than a screwdriver. A huge part of a programmer's skill is knowing the landscape of tools available and being able to pick the right one for the job at hand. It always, always comes down to that. And that brings me to one last kinda mind-bending thought to leave you with. We've spent all this time talking about building these complex bridges so we can speak the computer's language, but as computers and AI get smarter and better at understanding us, do you think a day will come when we don't need these bridges anymore? When we can just tell the computer what we want in plain English and it'll just do it? Something to think about.